Question 15, part A. So to work out I1, that's just In where n equals 1, so we just plug in 1 there. So x to the 1 is just x. And then the way that I like to think about this kind of integral is that I know it's going to involve 1 minus x squared to the 3 on 2, because that's what's going to give us the root 1 minus x squared when we differentiate this. But let's just think about what the derivative of this is so that we can see if there's any factors that we need out the front to compensate for things. So the derivative of this would be 3 over 2 times 1 minus x squared to that minus 1 is 1 over 2. And then there'll also be the derivative of that is minus 2x by the chain rule. So what that gives is that's going to cancel with that, and you're going to get a negative 3x root 1 minus x squared. So we don't want to have a negative 3 there, because there's no negative 3 here. So we have to put a negative third out the front to compensate for that and get rid of it. And then that's from 0 to 1. And this doesn't need to be part of your working, that's just in your head or in your rough working. Okay, and then we just plug those values in, so you can actually, let's put the negative third out the front of everything. I'll just make it simpler. So when we plug in the 1, that makes 0. And then when we plug in the 0, we get 1 minus 0, which is 1, and then to the power 3 on 2, that's still 1. So that just makes positive a third, because the negatives cancel. Okay, part 2. So they're suggesting we use integration by parts. So we want to integrate In, which was that. So how can we apply integration by parts to that? So we have to integrate one thing and differentiate the other. Now, my sort of line of thinking of this was that we want to be able to get an x to the n minus 2 when we do the integration by parts, because we need to involve In minus 2 somehow. So what we probably want to do is differentiate this one and integrate that one, because that's going to reduce the power. But we can't integrate just this bit, we have to do x times this, because if you remember in the last question we were integrating x root 1 minus x squared. So that we can do. So let's split this into x, so I'm just going to take one of these x's out from there. So this will be x n minus 1 times x root 1 minus x squared. And then we can integrate this part. So doing integration by parts, so leave that bit there, and then we'll have the integral of that, which you may remember from part 1 was negative a third times 1 minus x squared to the 3 on 2. So that'll be from 0 to 1. And then we want a minus integral from 0 to 1, and this is where we differentiate that part. So we'll get n minus 1 x to the n minus 2. So there's our n minus 2. That's good, because that's going to give us the In minus 2. Okay, and then just this bit. Alright, so let's work out what this is. When x is 1, you're going to get a 0 there, so the whole thing's going to be 0. And then when x is 0, that bit's going to be 0, so again the whole thing's 0. So all of this is just 0. And then let's bring the negative a third out the front so that those negatives will cancel. And we've got a third integral from 0 to 1. I could have taken that minus 1 out the front too. So we've got the x to the n minus 2. And then, okay, let's think about how we're going to deal with this power of 3 over 2, because we don't want that. What we want to have is something involving n minus 2, which is going to be x to n minus 2 times root 1 minus x squared. So what we could do with this is split it up into 1 minus x squared times root 1 minus x squared. And then hope that that works out somehow. We can deal with this 1 minus x squared. But at least now we've got a root 1 minus x squared in there. Okay, so actually I will take the n minus 1 out the front. And then we could split this up into two different integrals, because we've got, like, when we expand this, the 1 minus x squared. So we'll have integral from 0 to 1 of that one, and then minus. So the x squared times that is going to make x to the n. Okay, sorry if that was confusing for anyone. I've just sort of expanded this and then split it up into two different integrals. So this bit is I n minus 2. And this bit is actually just in. Okay, well that's really good. We've now got an equation just involving in and in minus 2. We just need to solve that for in. So we want to, like, bring all the in's over one side and then factorize and simplify and so on. But what I might do first, because I don't like dealing with fractions, so I might just multiply both sides by 3 to kill that. So we'll get 3 in on the left. And then let's expand this. So we've got the n minus 1, in minus 2. And then we'll have minus n, in, and plus in. And we do that times that. Okay, and then let's just move that stuff over there. And then this is just n plus 2 times in, and then we can divide both sides by n plus 2. And that will give us n minus 1 over n plus 2, in minus 2, which is what we wanted to prove. So that's it. Part 3. Okay, so we just proved that that was true, and then in part 1 we also showed I1 equals a third. So how can we use those facts to find I5? Well, what we could do is find I3 using this, because I3 is going to be 3 minus 1 on 3 plus 2 times I1, and we know what I1 is. So let's start by working out I3. Okay, so that's 2 on 5, and I1 is a third, so that's going to be 2 on 15. And then from there we can work out I5. Just plugging 5 into there, we get 5 minus 1 on 5 plus 2 times I3. So 4 on 7 times 2 on 15. So that makes 8 on 105. Part B. So we need to find dy by dx. The easiest way to do this is with this sort of equation is to use implicit differentiation, which just means that we differentiate both sides of the equation with respect to x. So this is x to the half. If you differentiate that with respect to x, you get half x to the minus half. Now this one, if you differentiate that with respect to x, then by the chain rule, you get half y to the minus half times dy by dx. Because remember that we're differentiating with respect to x, not with respect to y. So we've got to multiply by that. And then on the right, this is a constant, so its derivative is just 0. Now you've got this equation which you can solve for dy by dx. Now, because I've done that sort of differentiation 1,000 times, I would probably just go straight to saying it's 1 on 2 root x. So derivative of root x is that, but if you forget that, you can do it that way. So we get that, and then we can just rearrange things to get dy by dx. So subtract that from both sides, and then divide by that. and then that will give you, well, it'll be 2 root y over negative 2 root x, and then the 2's will cancel. So we get negative root y over root x. Alright, and then what we want to do is work out the slope at that point. So the slope is going to be dy by dx when x and y are c and d. So you just plug those values in. So we get negative root d over root c. And then we can use, y minus y1 equals x minus x1. So y minus the y1 is just a point that's on the line, which would be d. Times x minus x1, which is c. And then we just need to rearrange this until we get something that looks like that. So let's multiply both sides by root c. And then they've got the x and y over the left and all the constants over the right. So let's just shift that over there and shift that over there. That's it. Part 2. So I just want to give you a graphical idea of what's going on here. So we've got this tangent line which has that equation. It's, going to look like whatever. And then it's saying that it meets the x and y axes at a and b. So that's a and that's b. And we need to find the distance OA and the distance OB and add them up. So we just need to find basically the x and y intercepts of that line and add them. So at A, you'll just have that y equals 0, and then you can plug that in there and, solve it for x. So you get x root d is d root c plus c root d, and then we can divide both sides by root d. Okay, so you get d divided by root d, which is just root d. So root d times root c, and then that divided by root d is just c. And at b, that's where x equals 0. So plug x equals 0 into there, that bit disappears, you get y root c is d root c plus c root d. Divide both sides by root c to find y. And then I'll just cancel with that for that bit. And then you'll have c divided by root c, which is just root c. Okay, so what we've found here is actually, this is OA, because it's the x coordinate of that point. So this is OA, and this is OB, because that's the y coordinate here. So that distance is the same as that. And we just need to add those up. So OA plus OB. And that's the same as that, so let's collect those together. So you'll have c plus 2 root c root d plus d. And then we have to show that that equals a. So let's think about how a is going to become involved in this whole thing. So the only information we have so far that involves a is that. So that should give you a clue that what we have to do is use the fact that this point is on the curve, meaning that this point satisfies this equation. So you could say something like P is on the curve, therefore we can plug those values in there and you get root C plus root D equals root A. So what we need to show is that that equals A. So what we could do is just take this equation and square both sides. And then on the left, actually let's just show what we're doing. And then that will become C plus 2 root C root D plus D when you expand it. And then we showed that that was array plus OB. So that's it. Part C. So this point P x1, y1 is where they both meet. So it's kind of like solving these two equations simultaneously because they're both going to hold true at this point, except that we don't actually want to solve it for x or for y. We just want to take the two equations and manipulate them until we can find x1 over y1. So let's see what we can do with these. One simple thing that we could do is just, because both of the right-hand sides are 1, we could just say that that equals that at this point. So we can say, okay. And then, personally, what I would do with an equation like that is just multiply everything by a squared, b squared, c squared, and d squared, because I don't like having fractions in my equations. I find them messy. So let's do that. Alright, and then what we could do is move all of the x stuff over one side and all the y stuff over the other side. So I'll move that over there and move that over there. And then let's divide both sides by that and divide both sides by that. So that we get that, which is what we're trying to find. Okay, and let's factorize this as well, because we've got an a squared and a c squared in there. So that'll be negative a squared c squared times b squared plus d squared. And so we'll have it over this, but let's factorize this as well, because we've got a b squared d squared. Take that out the front, and we're left with c squared minus a squared. Okay, so now we're quite close to what we want. We just need to, what we can do is like multiply top and bottom by -1 to shift that down, and then the negative of this is actually a squared minus c squared. So that'll give us, and then let's split it up into 2 fractions like that. Yeah, and then that gives us what we want. So that's it. Part 2. I'll just put the result from part 1 there, because we're probably going to need that. Now, the plan for this one is that we work out the slopes of the tangents, and then show that they multiply together to make -1. So that'll show that they're perpendicular. So we need to differentiate these 2 equations to work out the slope of the tangent. And we also need to use this fact that they have the same foci. I'll come to that in a minute. But okay, let's start with working out the slopes of the tangents. So for the ellipse, we differentiate this using implicit differentiation. Our derivative of 1 is 0. And then we rearrange this to find dy by dx. So I'll subtract that from both sides and then divide both sides by that. And then at the point P, which is at x1, y1, we're going to get, so we just plug x1, y1 into there to find the slope. And I'm going to call this E for ellipse, because we're going to find the slope of the tangent of the hyperbola as well, and I don't want to have them both be called M. So that's going to be negative x1 b squared over y1 a squared. Okay, and then for the hyperbola, we are going to have, so differentiating both sides of that, derivative of 1 is 0 again. Now we want to solve this for dy by dx. So I'm going to subtract that from both sides and then divide both sides by all of that. And then at P, it's going to be, I'll call this MH for hyperbola, x1 d squared on y1 c squared. So now what we can do is multiply these 2, because if the product of these is -1, that'll show that the tangents are perpendicular. So we can say slope of the ellipse times the slope of the hyperbola. I mean negative, we're going to get x1 squared b squared d squared. So just that times that, and then on the bottom we're going to have that times that. y1 squared a squared c squared. Okay, now we're trying to prove that that's -1. So we're going to have to use this, and we're going to have to use the fact that they have the same foci. So let's plug this in. Okay, now we can do some cancelling, because that cancels with that, and that cancels with that. And we get negative b squared plus d squared on a squared minus c squared. Now here's where we need to use the fact that they have the same foci. So the distance from the origin to the focus for the ellipse is going to be AE, and for the hyperbola is going to be CE, because remember C was the number there. And so E is going to be root 1 minus b squared on a squared, and for the hyperbola it's going to be root 1 plus d squared on c squared. So we can just take that equation and square both sides, and we get that, and then let's just expand those. Okay, now what we need to find is b squared plus d squared over a squared minus c squared, so we'll just need to rearrange this a bit. I'll just move the c squared over there and the b squared over there, and then we can just divide both sides by the a squared minus c squared. Right, and then we can just say something like ME times MH equals -1, therefore the tangents are perpendicular. Okay, that's it for number 15. So let me know in the comments if there was anything that didn't make sense, and stay tuned for number 16. So you can subscribe and click the little bell if you want to get notified when I post new videos.